So the next talk in the industry session is going to be given by Luming Zhao, sorry, from IonQ.
Yes, thanks, Thomas. So my name is Luming Zhao. I work at IonQ as a researcher. So today I'll be presenting the application-oriented benchmarks for quantum computing. Okay, so here's the outline of the talk. I will start by discussing the power of quantum computing, and then I will talk about the needs for developing benchmark algorithms for estimating or measuring the performance of quantum computers, and then also track the performance gains as we continue to develop quantum hardwares. I will talk about existing quantum benchmark algorithms, and then we'll talk about the motivations for developing this development of these application-oriented benchmarks by the QEDC, which is a Quantum Economic Development Consortium. I will then dive deeper into the benchmark suite to talk about algorithms, metrics, and results on IonQ's previous and latest generation of quantum computers. And then I will switch topic to talk about algorithmic qubit, which is a single number metric to measure the performance of quantum computers and its rules and results on IonQ's latest generations of quantum computers. I will end the talk with conclusions and perspectives. So as we know that a quantum computer has power to solve many problems that are either intractable or difficult to solve on classical computers. And it has found many interesting applications in a variety of different industries. In artificial intelligence, it is capable of enhancing the accuracy of machine learning models that performs like image classification, generative machine learning, or natural language processing. In quantum chemistry, it is capable of helping like drug discovery, design of new materials and catalysts that help like climate change or search for renewable energy resources. In finance, like early use case of quantum Carlo sampling has found that it's capable of yielding like quadratic like speed up over classical counterparts. But in the NISQ areas, quantum computers are noisy, and the noises can arise from noises can arise from different sources, such as like qubit initialization, gate operations, and state readouts. So it's quite crucial to develop this benchmark algorithm to like really estimate or measure the performance of quantum computers and measure the performance gains as we continue to develop these quantum computers. So there are many efforts really being put into this area. And the most commonly used one is perhaps the quantum volume benchmark, in which you run these like a random circuit with random 2-qubit gates and measure the heavy output. And the quantum volume will be defined by the largest circuit we run successfully, both in terms of number of qubits and also in terms of the circuit depths. And another way to do this is to do this mirror benchmarking, in which you design a circuit in the mirror way so that the outputs are known, and then you measure the success probability of obtaining such outputs. Other benchmarks also exist, such as this one based on line drawing, which is to use quantum computers to draw like these more and more complicated shapes. And then you look at your measure result to see how similar that is to the original shapes. And these benchmark algorithms give you some information about the performance of quantum computers, but they do so in a very indirect way, because like as an end user or a customer, I'm more interested in like the performance of quantum computers that are run actual quantum applications. So the other difference between these random circuits and more structured circuits is that for a random circuit with all of these random like 2-qubit gates, and you really have this population of your state. Once you measure it, the population will spread out to all the like possible like bit strings. But for more structured circuits, on the right here, I show a VQE circuit. And once you measure it, you'll find that the population is more like structured and concentrated on like a few states. So it's quite different for like the measurement results for these random circuit and structured circuits. And as an end user, I'm more interested in learning like how a well quantum computer can perform from these structured circuits. So these two like factors basically motivates us to develop this application-oriented benchmark algorithm or benchmark suite. The goal is to collect a set of quantum algorithms that are either routines or subroutines of quantum applications, and then measure their performance through a set of different metrics and report these metrics. So here are three major parts of these quantum of the application like benchmark suite. The first part is quantum algorithms. So we include like Boyce-Razorani, quantum Fourier transform, and variational quantum eigensolver, a whole bunch of quantum algorithms. And the second part is metrics. The most important one is circuit fidelity, which just measures the success probability of the circuit that you run. And we also report timing, such as execution time and initialization times, along with other metrics, such as like circuit depths or 1 to 2 qubit gate ratios. And all of these code and algorithm are in this open source repository that everyone can just download and use it and contribute to it. So the most important part of this benchmark suite is the choice of algorithms. So we have like 3 different types of algorithms. The first type is like more of tutorial level of algorithms, such as, for instance, Rasmani, Dijkjosa, and hidden shift. So these are really like tutorial level algorithms that people use to show quantum advantage. And then they have like they also have very simple structures, like you initialize a qubit in some superposition, and there's an oracle, and you measure it. And then the second part is the subroutines of quantum applications, such as quantum Fourier transform, quantum phase estimation, and amplitude estimation. So these are like widely used in many quantum applications. For example, like QFT and QPE are used in like quantum chemistry for estimating Brownian energies for some molecules or materials. And the last type of it is actual quantum applications. So we include like Monte Carlo sampling, global search, DQE, source order finding, and Hamiltonian simulation. Like these are actual quantum applications. DQE or Hamiltonian simulation are used in like estimating energies of molecules, or to like model or simulating quantum dynamics. Monte Carlo sampling is used in finance for like portfolio optimization or risk analysis. So these are the algorithms that customers would like to run on a quantum computer. So let's now dive deeper into the circuits in the benchmark suite for these 2 particular algorithms. The first one is QFT. The QFT circuit pretty much looks like this. So first, like a secret integer is encoded into a bit string, and we perform QFT. And then we add 1 to the encoded integer, and we perform QFT inverse, and we measure the qubits. And on the bottom, I show a QFT, like a QFT circuit, which is done through this control rotations. As you know, that the output probability distribution of this type of algorithm really concentrates on just 1 bit string or 1 state. If the input is A, the output is going to give you A plus 1. So algorithm like this, with like populations concentrated on 1 or only a few states, include like, for instance, Masrani, QFT, phase estimation, Grovers, and Monte Carlos. Another type of circuits are the VQE circuits. For the VQE circuit in the benchmark suite, we implement this unitary coupled cluster with singles and doubles. The ansatz looks like this, like the exponential of t minus t dagger, acting on some reference state. The T operator is the summation of excitation operators in chemistry, and we truncate that to only single and doubles for the UCCSD ansatz. And the circuit looks pretty much like that. In the bottom, the qubit initializing Hartree-Fock state, and we perform the T operations. The first 2 correspond to singles, and the last one corresponds to a double excitation. And the fidelity of this circuit is actually measured using this so-called polarization fidelity. So we first compute the Hamilton fidelity, which measures the similarity between the probability distribution you measured on a quantum computer and the ideal probability distribution that you obtain on a noise-free simulator. And then these Hamilton fidelities renormalize or normalize to be within 0 and 1 using this uniform distribution. And as you know, that this requires you to know the ideal probability distribution, and these are pre-computed and stored. However, as the number of qubits get larger and larger, it becomes infeasible to simulate these systems on a classical computer. Therefore, this is not really a scalable approach, and future developments are needed. So algorithms like this contains Hamiltonian simulation and VQE in the current benchmark suite. So after the circuits are run, we plot this volumetric plotting. So here is the example of the volumetric plotting. On the y-axis, we have the number of qubits or circuit width. And on the x-axis, we have the circuit depth, which is the longest path of the quantum operations for qubits in the circuits, compiled in Rx, RY, RZ, and C0 basis. And the color for each of these blocks correspond to the fidelities of these circuits. For circuits like the QFT with like output population concentrated only a few states, the fidelities, the measurements or the fidelities reported as a success probability of finding like the truth. And for the circuits like VQE or Hamiltonian simulation, the fidelity is the polar resistive fidelity that I introduced in the last slides. So here I show the benchmark results on IonQ's previous and latest generation of quantum computers. On the left is the previous generation of quantum computers, which is available on all major cloud services such as like AWS, Google Cloud, and Azure. So, and on the right, this is a new result from IonQ area, our latest generation of systems. So on the left, you can see that it performed pretty well for these wide and narrow circuits, but pretty much reaches the limits once the like the depth of circuit exceeds 64. And on the right, you see that on the latest generation of system, we have significantly improved fidelities. We still perform really good for we still perform really good for these wide and shallow circuits, and then but with more qubits, like we tested for instance, running all the way up to 21 qubits. And the improved fidelity really gives us really improvements for these narrow and deep circuits. Like for amplitude estimation, this one we run up to 500 C0 2 qubit gates, and the fidelity is about like 40%. On the previous generation of system, you basically got zero fidelity. And we also see improvement for these like circuits like QIP or phase estimation that are in the middle. So the take-home message for that IonQ area offers more qubits. The time the benchmark will run, we test up to 21 qubits, and also significant improvement in fidelities, especially for these deep circuits. So now let's talk about the algorithmic qubit. So the volumetric plotting and the QEDC benchmarks will give you some estimation or some measurement of the performance of quantum computers. But unlike the QV benchmark, it does not give you like a single number. So here I introduce a single number, which is called the algorithmic qubit to give you like an overall estimation of the performance of quantum computers. So suppose this is a revised volumetric benchmarking plot. It is revised in a way that we change the x-axis from circuit depth to the number of 2 qubit gates. And then I draw a box on this plot with like horizontally the width of the vertically the width of the box is the number of qubits, and horizontally it is number of 2 qubit gates squared. And then the AQ is defined as the largest box that you can draw, the width of the largest box that you can draw, in which all the circuit inside the box pass the success criteria or meet the success criteria. Roughly speaking, if you have a quantum computer of A cube n, then you can say that this quantum computer can run the circuit with n qubits and n squared 2 qubit gates successfully. But the question is, what should the success criteria be, and what algorithm to use to measure success? So here, the VQ definition without any rules is pretty meaningless. And here I show the rule of AQ version 1.0. For algorithms, we include QIP, phase estimation, amplitude estimation, Monte Carlo, Grover's VQE, and Hamiltonian simulation. So as you see that compared to the QEDC benchmarks, which we exclude those like wide and shallow circuits. And then the circuits need to be transpiled into the same, like the basis, like Rx, Ry, Rz, and C0 gates to count the number of 2 qubit gates. The number of 2 qubit gate is essentially the number of C0 gates. And the circuit fidelity is measured instead of using like the polarization fidelity, we use Hellinger fidelity for this of the AQ measurements. And the success of the circuit is defined as the fidelity after you take into account of the statistical errors. The fidelity should be above the success threshold. So epsilon c there is the statistical error based on number of shots, and the t is the success threshold, which is chosen as 1 over e, which is like 37%. So here's two things I need to point out. So the AQ is really a measurement for the whole quantum computers. In terms of the whole quantum computers, we have input circuits, and the circuit compiler will come in and then transpile the circuit and optimize it, give you output circuits, hopefully with less number of gates. And then the circuit is now put into a quantum hardware to run, and then in the end, we can perform some error mitigations. So because we're measuring the performance of the whole quantum computers, we allow innovations in compilers. So compilers can do whatever it wants to reduce number of gates, as long as it is implementing the same unitary operator and as long as it is general enough and does not target any specific algorithms. And we also allow for error mitigation. So error mitigation is allowed as long as it is reported with the results and it does not require the knowledge of the output to be general enough. So here I show the AQ measurement on IonQ area with error mitigations. And then the measured AQ is 20, which means that on this quantum computer, you can run a circuit with 20 qubits and 400 C0 gates successfully. So the widest circuit we run successfully is the quantum phase estimation with 20 qubits and 380 C0 gates. The deepest circuit we run successfully at Monte Carlo sampling with 6 qubits and 478 C0 gates. And the error mitigation we use here is a technique called diversification, which is to exploiting the symmetry of the circuit's execution, because these symmetries do not require you to know the output. So it can be generally can be deployed to our execution layer. In this case, we use the ability to map the circuit to different qubits and then consolidate the result to mitigate errors. The more details of the error mitigation approach will come in an incoming paper. And then, so I will spend the last 2 slides talking about future developments of these projects. For the QEC benchmark project, one direction we're pursuing is to do a full implementation of these hybrid algorithms, which are most promising in this area. For now, we only implement the QPU part, but we exclude the classical optimization part. In the future, we would like to we would like to have a full implementation of both the QPU and the interplay with the classical optimizer. And then we also want to benchmarking execution time. So for now, the benchmarks we report execution time, but it's really hard to compare, to have an apple-to-apple comparison between different hardware makers. And last, for the algorithmic qubits, we certainly want to add more quantum algorithms to that, such as quantum machine learning and QAOA. And we need to find a scalable measurement of success probability for algorithms like VQE and Hamiltonian simulation. And in terms of circuit optimization, the question is how much optimization is allowed, especially for some type of algorithm. We can add an ancillary qubit, for example, to reduce the number of gates. And then how many ancillary qubits are allowed to add? And then that's an open question. And then in the end, in the future, if error correction become widely used, how would you differentiate between physical qubits versus logical qubits? So we hope that for now, AQ is just in the version 1.0. We hope in the future it will evolve and more algorithms will be added and more strict rules will be introduced, and AQ will be a routinely used measurement to measure the performance of the quantum computers. And I would like to thank all of these people. This is really a collaborative work. I would like to thank Ken, Kenisha, Neil, and Jason for running this benchmarking circuit, Andrea for developing and implementing these error mitigation techniques, Sonica for coming up with the AQ definition, and Johnson for leaderships. And we do have a research credit program that you can basically submit a small proposal and get $10,000 worth of machine time on our systems. And of course, thank you all of you for your attention.
Thank you. We have time for one quick question, if there's one. Yeah.
My question is about the decision to put software and hardware within the same benchmark. Does this prevent comparing just the hardware device performance, or should quantum volume be used for just hardware metrics? And does this impede the open sourcing of hardware agnostic compilation techniques, which otherwise have contributed a lot to collaboration, transparency, and educational efforts?
So the rationale behind that we're comparing this AQ measurement, or we're measuring AQ for the whole quantum system in terms both in terms of hardware and software, is because we are really customer focused. So customer does not really want to know what is going behind the execution of the quantum computers or what the compiler is doing. So they are really interested in knowing. So if I want to run a VQE circuit for some chemistry problem, for example, then how well this system will perform in terms of that. So So that's the rationale behind this benchmarking or measuring the performance of the entire quantum system that include both the quantum hardware and the quantum OS.
Thank you.
All right, let's thank Luming again.